everyone. So I'm going to go over the solutions to problems D and E from the center of mass homework, or practice I should say. So I've already written in some of the calculations, but I'll walk you through them and come into class if you have any further questions. Okay, so we have a two-dimensional situation here. We have an L-shaped made out of two uniformly distributed mass objects, regardless of what they are. One is 120 grams, the other is 80 grams. And you're given the dimensions. And we want to find a center of mass relative to this spot here, because it's probably the most convenient to look at. And so the hard part about this is just visualizing how each piece, where it is located in the x direction and the y direction. And in order to locate where it is, and you've got to remember these are masses that are extended in space, we've got to reduce each mass to one point, its individual center of mass. So I've got the green mark for where we're going to measure from. So let me use the red mark to indicate the center of mass for each object. So if I take the long 12 centimeter rectangle, it's going to be at the 6 centimeter mark. So that's its center of mass. And for the 8 centimeter 80 gram one, its center of mass is right here. So that I can compare those to the green origin to get my x and y coordinates. So the first coordinate is the x direction for the 80 gram. And it's already given as 5. So let's make sure we understand why that is. Also, I think this was given on the sheet, I hope, is that the dimensions of the width, this is 2 centimeters wide, and this is 2 centimeters wide there. Because without that information, you can't really proceed. Okay, so if I know that, then I know from here to the edge of the 12, so I'm moving in the x direction for the 80. I'm seeing how far, basically what I'm looking for is how far away is this dot from here. And it's 1 plus 4, so it's 5 away. Then I can ask, let me redraw this one, how far is this dot from here in the x direction? Well, since it's directly above it, it's not. It's 0 away. It's in the same location, at least as far as the horizontal direction is concerned. So if I now do the same thing for the vertical, for the 120 gram mass, wait a second, I got that backwards. I got the 0 should be right here. The 120 gram mass is 0 away in the x direction. So I can ask how far is the 80 in the y direction from 0? Well, the 80 is in line horizontally, so it's not above or below that. So that's also 0. And then how far is the 12 above here? Well, you'd be tempted to say it's 6 above, but remember from here to here is 1, so it's actually also going to be 5. So I know I got a mess right here. Redo that for yourself if you don't see where I came up with those numbers. Okay, now I can do the center of mass calculations for each direction. So for the x direction, I've got 5 times 80 plus 0 times 120 divided by the sum of the masses. And then when I work that out, I get a center of mass of 2. And then if I do the same thing for the y, right here are the calculations. I've got 0 times 180, 5 times 120 as my numerator, divided by the sum of the masses, and I get 3. So if I go over to my origin, and I go over 1, 2 roughly, then up 1, 2, 3, here is my center of mass. It's not on the body, but that's okay. It doesn't have to be. So that means is if that was an L-shaped object, I could not balance it on my finger if I were holding it because the center of mass is off. Next one is actually based on a lab we could do if we had the time. So I have a set of dowels, PVC, metal rod, and wooden dowel, where the metal rod and the wooden dowel can fit inside the PVC because it's hollow. And so I've drawn each one right here, and I believe on your sheet you have a better schematic than I do. And what we want to do is, below, I want to figure out what the center of mass of different combinations are. So in this one, for example, I've taken the wooden dowel and I've put it so its left edge aligns with the PVC, and part of it, since the wooden dowel is longer, the PVC sticks out. Now I know what's the center of mass of the system. In the next one, I've got the metal rod in the PVC. Metal rod's shorter, so that's why it looks like that. And then I put all three together, where I leave the metal rod right here, and then at the end of it, I put the wooden dowel, so it's protruding even further. And so you have 3 objects instead of 2. And if you know how to look at it properly, then this is not hard to do, but that's the challenge, is how to look at it properly. And to look at it properly, you just got to take each dowel or PVC pipe and reduce it to a single mass, a single point, the center of mass. So if I look at the lengths that were given of each one, and we're assuming they're all uniformly distributed masses, then the center of mass of each one is simply half their lengths, and that's where those numbers come from. So let me, for example, if I look at I'm going to use black for center mass. If I look at this green center object, where is it located? It's all located right there. So I'm going to reduce the PVC to that point there. I'm going to do the same thing for the metal rod, and I'm going to do the same thing for the wooden dowels. And those lengths are what, these center of masses are what given. So when I do combinations, this is how I do it. I take the wooden dowels, and if I'm going to take 0 as the left end, right, that's my reference point. If I look at the wooden dowel, this is its center of mass. In other words, the whole wooden dowel all along here can be reduced to that one dot. And that's what I want to look at. I don't want to look at the fact that I've got a whole length of it that is distributed throughout from the left. So I'm going to reduce it there. There's my wooden dowel center of mass. So how far away is that from 0? Well, that's simply if I go to the wooden dowel, that's 45.8. So there's my lever arm, if you will. And then if I do the same thing for the PVC, right, the PVC center of mass is located right about there. And so its distance from 0 is its center of mass, which is 30. So now I can do my calculation. So if I look over here, I've got the wooden dowel first, its length times its mass, plus how far the PVC length, not the full length, I should say, that how far the center of mass is from the left, times its mass divided by the sum of the masses. And if I do the calculation, I get about 35.3 centimeters. Okay, so if I were to use another color to locate the center of mass of the system, then if this is 30, and this is 45, it's going to be somewhere in here. Okay, so if I put my finger at that spot, those should balance. So it's the same idea for the metal rod and the PVC. The PVC is still 30 away from here, because that's where its center of mass is located relative to it. The center of mass of the rod is shorter, and it's only 15 away from the left. So if I go over my calculations, I got the metal rod 15 times its mass plus the PVC 30 times its mass divided by the sum, and I get 19.9 centimeters. So in other words, even though the PVC is 30 centimeters long, the center of mass is more close to the metal rod, and this is just to the right of the metal rod, because the metal rod has so much more mass compared to the PVC. And then lastly, for all three, it's the same idea. There's just one little trickier part, and that's for the wooden dowel. So I have the metal rod, there's my 15. I have the PVC, there's my 30. But for the dowel, I got to do two minor calculations. I have to find its center of mass. Well, you already know that. And that center of mass is, 45.8? So it's 45.8 from here to here. And I have to add to it this distance here, which is the length of the metal rod, which is 30. So in other words, my lever arm, or how far away the wooden dowel is from the left, is 75.8. So there's my 75.8 times the distance. Here are the other two contributions right there, divided by the overall, and I get 27.7 for my answer. So the center of mass is right around there. Okay, so hopefully this makes sense in hindsight. Come in with questions if you have any.